In modern physics, there is a famous, slightly cynical mantra for dealing with the quantum world: shut up and calculate. This directive has guided generations of scientists to treat quantum mechanics as a mathematical oracle, equations that reliably predict results while remaining silent on the nature of reality itself. This pragmatic approach has been a triumph for technology, powering everything from smartphones to MRIs. Yet, surprisingly, if you ask 10 different physicists what those calculations actually mean for the fabric of the universe, you will get 10 different answers. To understand why there's so much confusion, we have to look back at the physics we used to rely on. Under classical mechanics, the rules of motion laid down by Isaac Newton, the world makes intuitive sense. Look at this vintage photo. Every object here, the batter, the catcher, the ball frozen in midair, has a definitive state. At any given moment, that ball has an exact position and velocity. Our human brains evolved to navigate this predictable, macro-scale reality. We expect things to be exactly where we leave them. So when physicists finally zoomed in to the microscopic scale, the behavior they found felt entirely broken and alien. Down at the quantum level, the concept of a fixed position vanishes. An electron isn't a tiny hard sphere orbiting a nucleus. Instead, it exists as a diffuse probability cloud, which physicists describe as a wave function. A wave function is simply an equation that calculates the likelihood of finding a particle in various possible states. This leads to the standard dogma taught in most textbooks, the claim that the electron physically exists in all potential locations at once until a scientist measures it. To match experiments, physicists introduced a mechanism. The act of observation forces this sprawling wave to instantly snap into a single point. The wave function collapses. But think about what that implies. Why should a human observer, or a measuring device, suddenly rewrite the basic laws of physics? Does the universe really wait for us to look before deciding where to put an electron? This logical gap isn't a new problem. Back in 1927, at the famous Solvay conference, the world's leading physicists debated this exact issue. Many of them immediately recognized that adding a special collapse rule for human observation was a clumsy compromise. Albert Einstein was the loudest critic of this approach. He famously hated the idea of what he called spooky quantum magic. He demanded an underlying, logical reality that continued to function mathematically, whether humans were looking at it or not. Decades later, theoretical physicist Sean Carroll presents a compelling argument in his book Something Deeply Hidden. He asks a pointed question: what happens if we stop making excuses for the oddities of quantum mechanics and just take the core mathematics completely literally? Carroll advocates for an approach called austere quantum mechanics. The word austere here implies a strict exercise in subtraction. We keep the foundational math, specifically Schrödinger's equation, which perfectly predicts how waves evolve, but we completely delete the arbitrary rule about wave collapse. By removing human observation as a special physics-altering event, we force the raw math to reveal what the universe is actually doing on its own. Let's run a theoretical experiment using these strict, austere rules. Imagine an electron existing in a pure wave of probabilities. According to the math, it is in a state of superposition, simultaneously holding two conflicting states. For example, one part of the wave represents the electron spinning up, while the other represents it spinning down. Now introduce a measuring device. Because we deleted the collapse rule, the electron's wave doesn't snap into a single state. Instead, the wave of the electron simply interacts with the atoms of the measuring device upon contact. This merging is a process physicists call entanglement. The electron's mathematical wave and the device's mathematical wave have inextricably linked together to form a single combined system. And the math doesn't stop at the machine. The human scientist reading the device is also made of atoms governed by quantum mechanics. The entanglement chain continues, pulling the physical matter of the observer directly into the exact same wave equation. If you follow the math without adding any special exceptions, you arrive at a startling conclusion. Because the initial wave never collapsed, the scientist is now mathematically entangled in a superposition, technically observing the electron spinning up and spinning down at the exact same time. If you're following the logic, you'll immediately spot the problem. If a scientist is technically in a superposition, why do human beings only ever experience one single definitive outcome when we run an experiment? In 1957, Hugh Everett proposed the many worlds interpretation. This framework accounts for our singular everyday experience while leaving the dual-state math of the quantum realm untouched. Everett realized that we don't feel a superposition because the universe resolves the conflict by branching. When the observer entangles with the dual-state electron, the universe literally splits, creating two distinct, mathematically isolated, parallel realities for each possible outcome. This even explains the famous Heisenberg uncertainty principle, the rule stating that you cannot simultaneously know a particle's exact position and its exact momentum. Those properties don't exist perfectly at the same time, because the universe actively branches to accommodate whichever specific property is measured. Certainty only appears after the split. Within this framework, the multiverse is an unavoidable consequence of a universe that resolves superpositions without collapsing its waves. It is easy to dismiss the many worlds interpretation. People often assume the idea of parallel universes is just a wild fantasy, cooked up by physicists wanting reality to feel like a comic book. But the opposite is true. Many worlds is arguably the most conservative, mathematically pure interpretation of physics we have. It requires the fewest assumptions, precisely because it refuses to invent new, magical rules about human observation. When you accept the math, the scale of our reality becomes breathtaking. Every single microscopic quantum interaction, whether it happens deep inside our own bodies or in the fusion engines of distant stars, forces the universe to quietly split again and again. The solid, predictable space we think we navigate every day is merely a localized illusion. We are just riding along one specific branch. The ultimate, absolute reality of the cosmos is simply one endlessly branching, majestic wave function.